Azimuthal-Radial.
就是要找那个补习班的老师之后一个，那你先学Petrašinović。
这个是把一个方面都有忘之后的话，然后下一个就是拿它们走。
I'm ready to start whenever you are.
Okay. Problems?
So, hello, my name is Petrašinović and I'm from Team Serbia, and now I will present you my team solution for problem number 11, Azimuthal-Radial Pendulum. So, the problem states that we need to design a pendulum that has a rod fixed to a stand, it has elastic rod fixed to a stand, and the end of that rod is connected to the stand, so we do not have vertical deflection of that rod. On the other end of that rod is connected a pendulum and that oscillations of that pendulum can spontaneously transfer from radial to azimuthal and vice versa. We need to investigate parameters of this phenomenon. So, what is actually happening in this problem? So, due to the movement of the support point, oscillations can transfer from azimuthal to the radial, and with respect to the system parameters that we choose, there can be one, multiple, or no conversion of axis at all. So, we are going to include some assumptions for our theoretical model. Is that we are representing elastic rod as a firm rod that has a joint connection to the stand, in which it is placed a torsion spring, and Bob is a small sphere, so it can act as a simple pendulum, and the strings that we are using to make the pendulum are not structural. So we can first write the coordinates of our Bob, x, y, and z. From those coordinates, we can calculate kinetic and potential energy by calculating the derivatives of those functions and their values. By calculating the drag force that acts on our pendulum, we can write equations down for the generalized forces that act on this pendulum, and substitute them into Lagrange equations of second kind. We derive a system of two differential equations that describe the motion of pendulum in our system. So, if we use small angle approximations for angles theta and phi, where theta is angle of deflection of pendulum, and phi is angle of deflection of rod from its equilibrium position, we can write a system of differential Lagrangian equations as follows from equations 1 and 2. When we solve that system numerically, we can get values for angles phi and theta. And also from these differential equations, we can see what are the relevant parameters of the system. So we have the length of the rod, length of the pendulum, L, length of the rod, L1, C, which is spring coefficient that is enjoined, M as mass of the pendulum, and we include the damping in our system. So first of all, we here have trajectory of the pendulum in ideal case when K is when C spring coefficient is large and we do not have damping, and also the pendulum is large and we are using small angle approximations. On figure 4 you can see the trajectory of the bob or the pendulum that we are following from OXY plane, and on the figure 5 you can see azimuthal and radial displacements of bob in time. Next, if we use a drag and we change them into our generalized forces. This is the simulation of trajectory of our bob with system parameters shown in the slide. So we see that bob, and that is the important point of our presentation, that we were investigating changes from azimuthal to the radial oscillations. So we see that bob starts from maximal azimuthal displacement, and because of the movement of the support point and damping, it is gradually changing axis to radial. So first, in investigating this phenomenon, we used next method. We were first analyzing the movement of bob through a simulation and through our experiment by recording the movement of bob from OXY plane. Then we were investigating for what combination of system parameters does this phenomenon happen. Why? Because we noticed during conducting our experiment that experiment does not happen for any arbitrary value of system parameters, so it only happens in discrete combinations of those values. And in our experiment, we were measuring converting time that was necessary to from axis to change from azimuthal to radial. Okay, so first this is our trajectory of our bob in experiment. As you can see, in the first couple of points, the trajectory of our bob in experiment is sort of bent and like racked. That is because the bob, we have camera that has constant frame rate, and the bob in initial second moves faster than it moves later. So we have same frame rate, but we have faster movement of the bob, and that's why our experimental trajectory in the beginning looks sort of racked. And we did that by analyzing the position of our bob in each frame. So as you can see, we process that in software tracker. So first, we'll show some results from our simulation. That is, we tried to make phase space for mass of the pendulum and spring coefficient of our spring. So we were trying to determine for which combination of mass and spring coefficient does this phenomenon occur. We set the range for mass from 5 to 140 grams. Torsion constant in range from, as you can see. And we said that phenomenon happen if azimuthal amplitude divided by radial amplitude is smaller than 0.01. Okay. So we can see that for white squares on this space that phenomenon occurs, and for the blue squares that phenomenon does not occur. So we can see that if we increase torsion coefficient, we are increasing the lower threshold for mass that was necessary to actually have this phenomenon. Second part was making that the same phase space, but for the length of the pendulum and length of the rod, which is L and L1. So rod's length was in range 5 to 45 centimeters. For this, that was range that we used in experiments, and that's some reasonable value for range. And length of the pendulum was in range 30 to 140 centimeters. As we can see, by increasing length of the pendulum, we are actually decreasing the upper threshold for length of the rod. So if we have a larger pendulum, we can use longer rods, and we have shorter pendulum, we have to use shorter rods. So in our experiment, we were measuring how the length of pendulum affects converting axis time. You can see the parameters we used for that experiment, and we were setting the phi angle of displacement of a rod in the initial moment to be 0. So we were trying to start from clear azimuthal oscillations. As we can see, we have here corresponding between the simulation and experiment. We were using small angles as well as our experiment, and we see that first of all, we can see that by increasing length of the pendulum, we are increasing the converting time, and that by using different masses of pendulum, as shown here, by the mass of the pendulum, we are decreasing that converting time. So we will test that later on. Now we're testing the effect of length of the rod to converting axis time. As in before, we used displacement of angle displacement of a rod to be 0 and displacement theta of our pendulum to be 10 degrees. Okay. So here you can see that by increasing the length of the rod, we are increasing the converting axis time, and as in previous plot, by increasing the mass of the pendulum, we are decreasing converting time. We can see that experimental values are within range of their errors, agreeing with values derived from the simulation. Now, we now want to try to investigate how the mass of the pendulum affects. We had fixed length of the pendulum, length of the rod, starting angles, and we were just varying mass. And as concluded from previous results, is that by increasing the mass of increasing the mass of the pendulum, we are decreasing converting axis time. So what we can conclude from the results we have is that we used that change of axis occurred only if amplitudes in both axes have a ratio lower than 0.01. We kept fixed all of our initial angles, and trajectory of bob derived by simulation is similar to the experimental one. And we investigated phase space of this pendulum by showing that phenomenon happens only for the thin combination of system parameters. Using small angle approximations, it gives us good agreement with our experimental results within the approximations we used. By increasing length of the string and length of the rod, we are increasing the converting time. Why? Because there is because if this acts as a simple pendulum, we have increase of the period in one axis, and we have the increased period in both axes. So if we are having combined oscillations, again, combined oscillation time is going to be bigger. And by increasing pendulum's mass, we are decreasing converting time. Why is that? Because larger mass makes a spring behave differently, makes it change its angle faster, and that's why we have the faster change between axes, because that time that was necessary from actual oscillations of the supporting point are important to how fast will axis change. So I'd like to thank you all for listening.
Okay, front, you have 2 minutes of clarification questions.
Could you please go back to the slide where you arrived at the origin?
Second. Okay, I believe that's
Yeah.
okay.
And what did you define as the azimuthal axis?
Azimuthal axis, as defined in the text of the problem, is the one normal to the rod.
Okay, cool. How did you release the ball?
We actually had made a cardboard, and we drew at a 10-degree angle, and we made sort of a little slope, and then we put our pendulum on it, and then just removed the cardboard.
Can you name one limitation of the assumption that you have proportional spring as your rod?
Limitation?
Just one limitation.
Well, yeah, torsional springs, well, because they read the angle, it is defined by the angle, and limitations could be because we used a very weak spring, that we cannot use very large masses.
Will your pendulum still convert if your rod is rigid? If your rod is extremely rigid, will you still get conversions?
Well, our rod is rigid, and it's just moving around the joint at stand. And I don't know if you think that if we have large spring coefficient, As I said, we have a phase space for which converting happens. So if we have a large spring coefficient, we will have to use large mass of the pendulum to actually convert.
What was the angle that you released the ball from?
10 degrees.
Okay, cool. Thank you.
Okay, in 3 minutes. Okay, thumbs up.
Good evening, everyone. I'm Opp. So I think that as a pundit, I should start with the problem statement because I think I missed it in the other PowerPoint. So it says fix one end of a horizontal elastic rod to a rigid stand, and it says support the other end of the rod with a taut string to avoid vertical deflection and suspend a bolt from it on another string. In the resulting pendulum, the radial oscillations, so ones that start parallel to the rod, can spontaneously convert into azimuthal oscillations, one that starts perpendicular, one that has turned into perpendicular to the rod, and vice versa. Investigate the phenomenon. So I think what was missing in some respect was a discussion of the phenomenon and like a clear reason as to why the phenomenon occurred. So the phenomenon here that's defined very clearly is the conversion from radial to azimuthal and azimuthal to radial, right? So I think that this really needs to be defined clearly, and we need to have causal links between the reasons. So I think that was one of the problems I had with the opposition's PowerPoint as a whole. In terms of the overall presentation, I thought that the definition and the phenomenology PowerPoint slide was really good. It set up the problem really well. The Lagrangian was also correct and very well set up. It was also very perceptive of them to note that the Lagrangian can only be applied in certain scenarios, and so they had to make certain assumptions with the coordinate system. Further, but I did find that the weaknesses of that page, statement of the problem was questionable. The elastic rod, there the problem says elastic rod, and we didn't really hear the limitations as such of their assumption. There wasn't an explanation of how some variables are kept constant, namely when you increase the rod and the length of the string. So I'll talk about that in discussion as well. But also the incorrect interpretation of the problem with the elastic rod and how that jarred with the whole, with their assumptions. But what I thought was, but the benefits of their PowerPoint were the fact that they had their simulation and that they tried the simulation with various initial conditions to see the effect. I also enjoyed the fact that they talked about the limitations of their experiment. However, I thought that there needs to be more reason given as to why, say, the orbits that they showed us were jerked and very sharp in their nature, when actually in nature we find that some oscillations in pendulums are very smooth. The last thing that I thought was really interesting was that they told us that the graphs they presented were quite different and allowed us to have trends that usually you wouldn't be able to see if you presented a normal graph. In discussion, I'd like to talk about the reasons for conversion, the limitation of the torsional rod and the validity of assumptions, the shape of the orbitals, so why it was regular, but also why they had elliptical orbitals, and also how tension, in terms of experiment, how tension was maintained in their taut string. So the problem states that you must have a taut string to prevent vertical deflection. I'd like to know how tension was maintained consistently throughout the experiment. And also what happens when you change the angle, and why does a vice versa conversion occur? So not only a radial to azimuthal y, but I also want to know why a azimuthal to radial can occur. And the last thing I want to talk about is the length of string graph. So if I'd like to invite the opponent of the discussion. So I guess the first question I'd like to sort of clear up is why we have conversion in the first place, right?
Well, we have most basic reason is that we have moving support point. When you don't have moving support point, but wherever you release ball, you're just going to offset demise. When you have moving support point, you get additional increase of the x and y values over the time.
Okay, so I don't particularly agree with that statement as you have moving support point, because initially, right, when you initially start your pendulum, the support point moving.
No, but
what reason is there for it to move? Does that make sense?
Inertia, because when you release the pendulum and it is movement of the pendulum. If initially we do not have movement of rod, it's causing the movement of rod.
Okay. Well,
it's like if you have a parked car and you crash it.
Okay. So I think that explanation is somewhat valid, but actually, because we have a velocity, right? Because we have problems moving with some velocity and some mass. I think that and an angular velocity as well. I think there might be an angular momentum there. And I think that's why you have why the rod will move in the first place, because it seems odd that the rod will start moving randomly, right? Like it needs to have some force acting on it to move, right? So which direction is the angular momentum vector?
Angular momentum vector is
just like, so sorry, if I have a if I have this, right? So if I release my pendulum here, right? Then which way is the angular momentum?
And you release it in this
side.
It should be coming out of the
page. So that's why that's why we have the conversion, right? We have the conversion from because it's pointing covered. So I think that should be cleared up. But then, so you told us that if we didn't have a moving support point, we wouldn't have the right. So if we didn't have a moving support point, then we wouldn't have conversion in the first place. Do you think that because of the way, if you think that's true, then if you know how we set up the Lagrangian as you have a point, and then it's got 3 different degrees of freedom each, right? So do you think that there's still an angular momentum vector pointing perpendicular if your rod is perfectly rigid?
Well, our rod is rigid, but it is moving.
So if your rod doesn't move, if your rod doesn't move at all, right? According to your Lagrangian, is there still an angular momentum coordinate system? Is there still an angular momentum vector pointing out of the coordinates?
Well, yeah, it is. It depends on from how you give it initial values of angle.
So if I was too excited, purely radially. Yeah.
Well, you wouldn't have that angular momentum vector. It wouldn't actually affect the movement of our rod. If you release it completely radically. And you can see that by, well, if you have conducted the experiment yourself, you can see that if you have a rigid rod or fixed that support point in vertical axis, you cannot achieve completely clean azimuthal to radial to azimuthal oscillation.
I think that you actually can achieve thing with a fix of the conversion with a fix of formation, and that's because you still have the angular momentum going this way, and so you have a torque. But we can come back to that because the other thing that was really good that I thought that was like you recognize that the Lagrangian can't be completed if you don't have rigid bodies in the system, right?
Yeah.
And because the beam is defined as being elastic, there's energy loss and deformation, so it's wrong to compute the Lagrangian for a elastic beam.
That is one problem with it. Another problem is if you have elastic rod, there is no actual relation that shows us how the angle of deflection of rod and linear deflection of rod connects. And even if we know that reflection, we cannot know potential energy of that reflection because it depends from the actual bending of the elastic rod.
Yeah, so I totally agree. But I was wondering, your assumption was that instead of the elastic bending, you have instead a torsional spring, right?
Yes.
And that it allows the rod to move back and forth. So that assumption means that it bends from the pivot. Does that make sense? It turns from the pivot.
If this is, let's say, axis of the pivot, our rod moves like that.
What's the difference between that and rotational kinetic energy?
How does it mean?
So it just rotates about that point. Why the angle? Why is it necessary for you to have the torsional spring?
We used angle in our Lagrangian because potential energy of the spring that we used can only be expressed if we have angle displacement.
Okay.
It cannot be connected to linear displacement.
So I think one of the ways we can improve,
It can, but it's not in.
yeah. I think one of the ways we improve the assumption,
Yes.
right, is we can actually make a rod instead of one torsional spring, different torsional springs. So if we have like spring and then spring, then that rod is now able to move in different, and is now able to bend like an elastic rod, but actually mimics the properties of a elastic rod. And that means that your torsional coefficient, because the springs are in series, the springs are in in the horizontal direction, it actually becomes 1 on K and not K. So it's completely different to having one big torsional
I
spring.
do agree that is possible, but that of course needs first experimental inspection to see that would actually result in more elastic movement if you need so.
So, but I think that because the rod statement has the word bending, it has the word bending, and the torsional rod implies a turning line of pivot. It's kind of counter to what the prompt statement.
that is true, but I'd like to have noted that effect is the same. Movement of the support point.
But because the spring coefficients don't add linearly, it's completely different having one big K, because it's now 1 over K or 1 over K.
Yeah, okay, well, we're using the K for our simulation, we are using that one in our experiment, there is no, I don't get the point.
No, I just that because if you have a torsional spring at the pivot, you're essentially rotating instead of bending. But I'd like to talk about the experiments that you did. So azimuthal, did you try releasing it azimuthally, if that makes sense?
Yeah, that's actually what we did. I said in my report that all of our measurements were done by releasing pendulum completely in azimuthal oscillations and then measuring time necessary from them to convert to radial.
Okay, so you released it azimuthally and you found that there was a conversion.
Yes.
Okay.
If you have some doubt, that I can clear it out because that's why we use spring with low spring coefficient.
Oh, okay, I see.
So we can achieve that.
So those bring up
And that's why we made phase space diagram and all other because we know that for certain values of spring there is just no conversion.
Okay, cool. You know the length of string graph, right? When you change the length of string, right? What do you think the limitations of that particular model are, considering the assumptions you made when doing these simulations?
Well, we actually haven't done it for
smaller.
We have done it for smaller, but we believe that at some point, because of that combination of parameters for which system doesn't happen, if we fix rod's length, at some point we are going to
string.
reach.
I mean the string.
I'm thinking about the experiment. If we fix the rod's length, at some point by decreasing springs, the pendulum's length, we are going to reach some value for which there is no conversion.
Well, I think a more serious or a better limitation is the fact that when you did Lagrange, you assumed the spring was massless, right?
Yeah.
So when you increase the length of the spring,
To some practical values.
it'll have a mass, and that will mean that you'll transfer momentum differently, and so the rod will bend less, and you'll have different conversions. So I think that's a limitation that wasn't discussed. So in terms of changing the angle, so you shoot a small angle approximation, right? If you had a larger angle, what do you think the effect of that on the path of the pendulum would be?
Yes.
So I guess the question I'm asking more specifically is, how would it dissipate the extra energy that you input in the system?
Okay, so first, if we actually done that in our experiment, just to see what and how the rod acts when suppressed to the initial angle that is larger. And for certain initial values, there is no much of difference. But if we increase that angle a lot, for let's say 60 or 90 degrees at least, a movement becomes more chaotic, and the support point does not actually, for masses that we use, it does not stand completely. It doesn't. It has vertical deflection.
Well, I think that the time taken for conversion would increase. But
Yes,
but that's it. I think we agree on that because of reasons. But I think the other thing is that if you increase the angle a lot, you said 90 degrees, right?
Yeah,
I think that because you have sine and cos ratios in your Lagrangian, 90 degrees won't work.
Yeah, it will change completely the way
it will change
the pendulum
Cool.
rotates.
The last thing that I was going to talk about really quickly is how you kept the tension in the string constant. So you know how the column is a taut string, right?
Yeah.
How did you keep that constant?
We made sort of a little
Okay.
So for every mass that we put, or for every rand's length,
Yeah.
we just connected string to the end of our stand and connected to that little
Yeah. So
rotating,
you had mass, okay.
and then we just attached string to the end.
So there was no
Okay.
vertical deflection.
Yeah.
The
And
last-
especially because the rod is rigid, there is no bending inside it.
You talked about your orbits, right? So at some point they were really pointy, like sharp,
Yes.
and at other points they were smooth and elliptical, right? So why do you think you have elliptical orbits in the first place?
Well, elliptical orbits come from different oscillation frequencies for both rod and our pendulum.
I actually think that that's not correct. I think the oscillation frequency is that you have angular velocity in the direction you released it, and you have a 90-degree phase shift in the angular velocity because you have a vector angular velocity perpendicular to the angular momentum vector. Because you told me that there was angular momentum,
Yes.
which means there's angular velocity parallel to that direction.
Okay, but that
Time's up.
doesn't give explanation for shape of it.
Okay, cool. We've got 1 minute. Very nice.
I think that the discussion was quite productive because I was able to discern things to do with how they kept experimental things constant. So one of the things I was concerned about is for example, the small angle. And so I asked them in question time, 10 degrees. And that was really important that they picked 10 degrees because actually the small angle approximation kind of breaks down at certain angles and so on. But I found it good that we were able to pick apart some assumptions of the Lagrangian and discern how effective they were in actually not only in answering the problem, but also answering the problem to the best that Lagrangian can do, because Lagrangian is inherently limited in its ability to model situations because you can really only model rigid objects to rigid bodies. So I think that was a particularly good assumption that they made, and the correction that was really good too. A point that I didn't get to was the shape of the orbits, and I think that needs to be discussed further, but I do think it's a result of the angular velocities. So thank you.
Okay, so the first question is for the reporter. How did you define radial and azimuthal? Because at what point is azimuthal and at what point is radial?
How I define radial and azimuthal displacements, or what? Or axis?
Just like when you are as we can see on the trajectory, it's really a kind of like an oval. So how do you define that it is azimuthal or it is radial?
Well, we have azimuthal axis that is normal to the rod, and radial that is parallel to the rod, and that's.
Okay, thanks. Then how do you avoid vertical deflection?
We use torque spring, and in the way that we were discuss just minutes.
Yes, do you have any data that you can show that there's really no diversion in z-axis?
Okay, so we should have, yeah, okay. You have a little like a arm branch here,
Okay,
and we just connect.
The next one, you mentioned that you release azimuthal direction. So what will happen when you create from radial oscillations?
If we try from radial oscillation, well, as again discussed, we cannot have simply total conversion from clear radial to azimuthal because we are using a rigid rod.
Okay, so when you are doing the experiments, did you control the azimuthal oscillation to pure azimuthal?
Yeah, we tried to make them pure azimuthal, and we tried to do vice versa conversion from radial to azimuthal, and it was possible just when we had that it is not in start, it's not solely radial, it has little of azimuthal displacement, then it is possible.
Okay, the next part is about the theory part. That
Okay.
do you think there's any time that the string will be loose?
I don't. Theory, is that?
Yes.
Okay.
Do you think there's any time that that the string will be loose?
The string would be.
The string that connect the ball will be loose
Okay.
instead of taut. Do you think there's any time that?
Well, it would happen only if the mass of the pendulum is really low. If we don't have actually great mass, but at that point, conversion wouldn't even happen.
Okay, and for the opponent, do you think there's any other dissipation that the reporter didn't take into consideration?
Sorry, can you repeat that?
Sorry, is there any other dissipation factor that the reporter didn't consider?
I think that the taut string, the bottom, the string that connects the bulb to the rod will not always be taut. And I think it's one of the reasons for the conversion, but also the momentum transfer between the ball and the rod is not conserved because of the string.
Okay, thank you.
Students.
Taiwan and now reviewing part number 11 Azimuthal-Radial Pendulum. So I believe the main focus here is that you use a elastic rod, so we should explain how it affects the phenomenon and also to we should explain the mechanism of radial azimuthal oscillations, conversion, and then the effect of every parameters. And then for the reverse outline, first in the observation part, you talk about the movement of the support points that cause the conversion. Then it depends on some damping. But I believe there's a clear video, but there's no video that demonstrates the observation. And then for the theory part, you use the Lagrangian and also the torque to find out its mechanism. But we believe there's no justification for some small angle approximation. And then for setup part, you use a video track to find the coordinates. But we believe that the children spring to use the children spring to approximate the elastic rod and also cast wide range of the parameters. But there's some concept the children has some error, large error, but it didn't explain why. And also they never changed the initial angle, which should also be a parameters. And then for conclusion, experimenters fix theoretical the simulation, but do not explain some of the error. And so for the opponents, he mentioned about some experimental details and also clarify the concept and also some talk about the limitation, which is quite important. And then they point out some quite important points. Sorry. And for the discussion, first I talk about the fixed support point, and the opponents think that the converging is it is fixed, and the first thing that is impossible to convert, and the bending and torsional spring are equivalent. And then for reverse, we agree with the opponent that the roll bends is because of elasticity, so that should be taken into consideration instead of just using the torque. And that is just an approximation. And then we also talk about the mechanism of the conversion, which the opponent talk about the transforms because of the angular momentum vector primarily. But the reverse is that bending caused by the moving point support, and the reverse is that we agree with the opponent, both momentums are quite important. And then we talk about the small angular approximation, and the first thing that their experiments is not no significant enough. And the opponent talk about what will happen if there is a wider angle range. And we think that you could just know the assumption by actually testing different angles. And I also talk about the effect of the length of the rod, which we agree with the opponent that larger lengths will cause greater dissipation and should be described in the theory. And the reverse asks about some experimental details and also some what the situation under pure radial and azimuthal situation and some other dissipation. Okay, so for some pointers, first the reverse believes that they should test some different angles that are other than the 10 degrees because that we might be able to find out some trend related to these parameters. And also one is the clear boundary when it transition between the azimuthal and radial because it only shows some of them. And did not clarify some problem with the Lagrangian, which we should consider the 3D coordinates. Thank you.
Hold on, we have 2 minutes.
Okay, I'd like to thank both the opponent and the review for great remarks that were considering my presentation of this problem. So first I'd like to say that in our experiment we were using small angle approximations that turned out to have good corresponding with actual experimental trajectory and experimental values. And then we used simulation to obtain phase space of this phenomenon, aka for what combination of relevant system parameters can phenomenon actually happen. Then we investigated how those phenomena affect the converting time of that was necessary for pendulum to go from azimuthal to radial oscillations. We were testing only conversion from azimuthal to radial. Opponent gave quite a few good remarks about the fact of us using torsion spring, and we think that there was discussion about the reasons for conversion, and I do agree with him that actually also the angular momentum is important for this conversion. He's asked about the limitations of string lengths, which I also think that is a correct statement, that there is actually some limit for which you cannot actually apply our approximations. Then it was insisted on testing larger angles. We did tested them just to see how much of the actual much of actual effect they had. But for measurements and for our conclusions that we derived, we were only fixing our initial value for angle. And there was a discussion about elliptical orbits, and I think that is a valid point that both angular momentum and momentum are responsible for that shape of the orbits. And I would like to thank them all for a great discussion, and that would be all.
Yes. Time for jury questions.
Maybe first, how did you measure and calculate the time of conversion?
We measured, we recorded our pendulum from OXY plane, so from top basically. And then we tracked its X and Y coordinates. Tracker is posted, and we have dependency of X coordinate in time and Y coordinate in time. And then we just written a simple program that gives us the converting time when azimuthal displacement divided by azimuthal amplitude divided by radial amplitude is lower than 0.01.
Okay, and how did you calculate it in the simulation?
That was also for the simulation.
Okay.
Well, the experiment to report that. How do you decide the installations?
I think that was some mentioning in discussion. We used cardboard and we drawn on it 10-degree angle, and then we made sort of small slope, and we put our pendulum on that slope, and then we just removed cardboard, and that's how our oscillation started.
Into the recorder. How did you measure the coefficient of damping?
We just used the simple mathematical pendulum to calculate its damping. So we were just having the fixed rod. It wasn't oscillating, and we were just releasing our pendulum and seeing how much energy is lost in one cycle.
Turn to a follow on from that. Just to follow on to that question,
Okay.
are there any other damping effects that would happen in the pendulum that don't happen in a simple pendulum?
More dampings. Well, all the dampings are actually caused by the sum of oscillations in both axes. So one displacement in one axis is decreasing because displacement in other is increasing, if that is what you ask.
Yeah. Is there anyone else who would like to ask? No? Okay.
Could you go back to your slide where you show your first simulation? Yes,
Uh,
it's like two
phase,
triangles against each other.
And I need to make
The first
clarification.
simulation.
This was actually a chip, but it's not working for some reason. Okay.
This one.
Okay, here.
This one. Am I right that the length, maybe just a distortion of the picture, but it seems like that those are triangles, which means that the length of the motion is changing with time. Sometimes it's longer, sometimes it's shorter. Could you explain it? Maybe?
Well, this was simply ideal case for most ideal set of parameters when we wanted to show just that the project can be completely like cross-shaped. And we use large values for torsion spring, large values for mass, and large values for pendulum slant.
Thank you. We've got 45.
If you're thinking about, I think that they're same x and y axis. That is another part of the question.
What about like, at 45 degrees,
Well,
and when it's like halfway through, that looks shorter
Yeah.
than it is at the ends.
maybe because of the picture making in PowerPoint, but the values should be the same.
Okay. Could you go to slide 17, please? Could you just put 17?
17.
I just want to ask, like, in every case here, your experimental data is all above.
Yes.
Is there got a simple reason why do you think they would all be out in the same way?
Well, there is the simple explanation that we use small angle approximations and 10 angle degrees, and they do vary a little. So maybe our measurement is that's why it is higher than. It is sort of systematically higher than simulation. And of course it can be because of actual measurements of the length of the pendulum or length of the rod or torsion coefficient of our spring. It can be, there are various causes of errors.
Okay, thank you. Okay, question time's over, so we will now decide on this.